Hello everyone. So in this video, we can wrap up integration by partial fractions by finishing the last two cases, case 3 and case 4. So in case 1 and case 2, we saw what to do if the denominator contains non-repeated linear factors or if it contains repeated linear factors. But remember, the full factorization can also introduce these irreducible quadratic terms, which look like ax squared plus bx plus c with b squared minus 4ac less than 0. And these are ones that we can't factorize anymore, so we need to understand what to do in those cases. Case 3 is going to be when we have terms that are irreducible quadratic that are not repeated. And then case 4 is going to be terms that are irreducible quadratic and are repeated. And case 3 is going to appear pretty often, so we have to be comfortable with that. But case 4 is a little, I would guess, a little more infrequent. Okay, so let's get started. So we suppose that step 1 and step 2 in our partial fractions algorithm is complete. So step 1 means that our rational function is proper. Otherwise, we had to do long division. Step 2 is that the denominator is completely factored into these linear and irreducible quadratic terms. So let's suppose that we're in case 3, and case 3 is what happens when the bottom contains an irreducible quadratic factor ax squared plus bx plus c, and it's not repeated. So, and none of them are a constant multiple of any other. So we don't have ax squared plus bx plus c squared or anything like that. We just have one of them. And in those terms, we don't have constant divided by ax squared plus bx plus c, but we have constant times x plus another constant over ax squared plus bx plus c. So these irreducible quadratics are a little bit different to the linear terms we had. For the linear terms, we always had constant divided by the linear term in case 1, or constant divided by powers of the linear term in case 2. Here we have constant x plus constant to deal with these irreducible quadratics. So for instance, suppose we had x over x minus 1, x squared plus 1, x squared plus x plus 1. This is for sure proper, so we're done with step 1. It's also completely factored from step 2. For instance, we have a quadratic x squared plus 1, but this is irreducible because b is 0. So b squared minus 4ac would be minus 4, which is negative. Or if we look at x squared plus x plus 1, it's irreducible. If we look at b squared minus 4ac, that would be 1 minus 4, that would be minus 3, that would also be negative. So this is, we're done with step 1, step 2. And now we have these quadratic terms that are irreducible and non-repeated, so we have to see what to do. Okay, x minus 1 is a case 1 term. It looks like constant divided by x minus 1. X squared plus 1 on the bottom gives us a case 3 term. We're going to get constant times x plus constant divided by x squared plus 1. And then x squared plus x plus 1 is going to give us another case 3 term. We get constant x plus constant divided by x squared plus x plus 1, where a and b and c and d and e are constants that we would have to solve for. Okay, but in practice, we're just going to have probably 3 constants at most in examples we'll actually work out. Okay, so that's the idea. By the way, how do so we get terms that look like constant x plus constant divided by ax squared plus bx plus c. So these are our partial fractions form. Why is this actually useful? How do we integrate this, right? The whole point of this thing we're doing is to help us integrate stuff. So if we're saying this is going to be useful, we need to be able to integrate things that look like that. So what do? Well, the strategy, as we'll see in 1 or 2 examples, is to first get rid of this x term in the middle. So instead of having ax squared plus bx plus c, we want to have something that just looks like x squared plus a squared on the bottom. And to do that, we can complete the square on the denominator and make a substitution. So once we go through those steps, it'll bring it to ax plus b over x squared plus a squared, possibly with different constants. But we can always get rid of that middle x term by completing the square and factorizing and substituting, as we'll see in an example in just a little bit. And then this one we can integrate by splitting up along the numerator. Remember, we can always split fractions along the numerator, but not along the denominator. And then we can integrate ax over x squared plus a squared just by substituting u equals x squared plus a squared. Because the derivative of this substitution will be 2x. Okay, there is 2x up to a constant multiple on the top. So that means substitution is going to work out nicely. And then for the other term, b over x squared plus a squared, we can use the fact that the integral of 1 over x squared plus a squared is 1 over a arctan of x over a. Okay, so at the end of the day, these terms that we get, we have to possibly complete the square and make a substitution to get rid of the x term. Then we split along the numerator. The one that has the x on the top, we can use a naive substitution. The one that's just constant over x squared plus a squared, we have to use arctan. Okay, so let's see some examples. For instance, let's look at, say, the integral of 2x squared minus x plus 4 over x cubed plus 4x. So step 1, it's proper. Step 2, we have to factorize the bottom as much as possible. So x cubed plus 4x, we can see straight away that x is a common factor. So we can pull out the x. It becomes x times x squared plus 4. And then x squared plus 4 is fully factored. So for instance, b is 0, a is 1, b is 0, c is 4. So if we do b squared minus 4ac, we're getting 0 minus 4 times 1 times 16. So minus 64, but definitely negative if you check. So it's irreducible quadratic, so we have to use case 3. So that means we have to find a and b and c so that this equation is true. So the x term is going to give us a case 1 term, right? It's a linear term, it's non-repeated, we get constant over x. And then the x squared plus 4 gives us a case 3 term, we have to have bx plus c over x squared plus 4. So we have to solve then for these constants a and b and c. So we would follow the same steps as we've done in case 1 and 2. So we multiply by x times x squared plus 4, then we sub in different values of x. In this case, there's only going to be one natural value of x, which is x equals 0. That's going to make things go to 0. And you would have to just substitute 2 more values of x. So if you have 3 unknowns, you need to substitute 3 values of x to find the constants. But I'm going to skip over that, maybe do some examples in class because it's just solving simultaneous equations. So if we do that, we get a equals 1, b equals 1, and c equals minus 1. So instead, we can integrate, if we substitute a is 1, b is 1, c is minus 1, we're integrating 1 over x plus x minus 1 over x squared plus 4 dx. And the bottom here, x squared plus 4, does not have that x term, so we don't have to complete the square or anything like that I was talking about on the last slide. We just have to split it along the numerator. So we have the integral of 1 over x, and then we split this fraction along the numerator. We have x over x squared plus 4 minus 1 over x squared plus 4. And then we integrate each term separately. The integral of 1 over x is just ln absolute value x. The second term, we could substitute u equals x squared plus 4, and the answer will turn out to be a half ln absolute value x squared plus 4. For instance, if you want to check by using the chain rule, if you differentiate ln absolute value x squared plus 4, you would get 1 over x squared plus 4 times 2x, which is the derivative of the inside. And then we multiply by the half. That will cancel the 2. We're left with x over x squared plus 4. And then lastly, the minus 1 over x squared plus 4, that fits into 1 over x squared plus a squared with a equal 2. So that's going to be a half arctan x divided by 2 plus c. Okay, so this was the strategy for case 3. Let's see one example where we have to complete the square to get rid of that cross term. So for instance, let's look at x plus 4 over x squared plus 2x plus 5. So it's a rational function, it's proper, so step 1 is done. We have to check the bottom is fully factorized. So if we look at the bottom, b is 2, so b squared is going to be 4. 4 times a times c is going to be 4 times 1 times 5, it's going to be 20. So we have 4 minus 20. The bottom is negative, so it's irreducible quadratic. So that means we have to just integrate it because it's actually already in partial fractions form. Right, there is just one term on the bottom. It's an irreducible quadratic term. This is actually already a partial fractions form. So let's complete the square to get rid of that x term. If we want to complete the square on x squared plus 2x plus 5, that's x plus 1 squared plus 4, depending on however you'd like to complete the square. If you multiply out x plus 1 squared plus 4, we get x squared plus 2x plus 1 plus 4. Okay, we get x squared plus 2x plus 5. And now we substitute u equals x plus 1. So let's substitute u equals x plus 1 and then du of dx equals 1, so du equals x dx. And we have to write everything where there was an x, we have to replace it by u, and everywhere there was a dx, we replace it by du. So at the bottom, rather than having x plus 1 squared, u is x plus 1, so we get u squared. So the bottom becomes u squared plus 4. And then on the top, x becomes u minus 1, so we are getting u minus 1 plus 4, so we get u plus 3. And then, okay, dx was equal to du, so that one is easy. And now notice that we got a term that looks kind of like what we had before, except this x term that was hanging out in the middle has disappeared. We don't have just a u term. The bottom is now u squared plus 4. So that made things simpler. And now let's split along the top. So we get u over u squared plus 4 plus 3 over u squared plus 4. And now we integrate each term separately. So if we integrate u over u squared plus 4, this is going to be a half natural log of the absolute value of u squared plus 4. Though the inside is positive, so we can then drop the absolute value. And then on the second term, we are using, again, the arctan formula. It's going to be 3 over 2 arctan of u divided by 2 plus c. And then as usual, on the last step, we did a substitution, so we have to write back in terms of the original variable. U is x plus 1, so we replace everywhere u by x plus 1. Okay, so with these ones where we have an irreducible quadratic term and the x term is still there, after we put it in partial fractions form, we complete the square, we make a substitution in u, we get rid of that pesky x term that was in the middle, and then we split along the numerator, and each of those terms we can actually then integrate. Okay, so let's finally look at case 4. So case 4 doesn't happen quite as often, but we still need to be aware of it just in case it does happen. So case 4 completes the picture, right? Remember we said that the bottom, after step 2, the denominator q of x should be fully factorized into linear terms and irreducible quadratic terms. And the only thing we didn't talk about is what we should do if there is a quadratic term, an irreducible quadratic term that is repeated. So it looks like ax squared plus bx plus c to the power r, where b squared minus 4ac is less than 0. And in this case, it's kind of like a mishmash of case 2 and case 3, and that it's kind of like case 3 because we're going to have constant x plus constant divided by our term. But it's not just going to be divided by our term or our term to the power r. We're going to have several different types of terms divided by the appropriate powers of our factor. So what do I mean? So if we have a repeated term ax squared plus bx plus c to the power r, we're going to have constant x plus constant divided by our factor, plus constant x plus constant divided by our factor squared, all the way up to constant x plus constant divided by our factor to the highest power. So here's, for instance, an example. So it's proper, and the denominator is fully factored. It's x minus 1 squared. So we have a linear factor, we have a repeated linear factor. Then we have x squared plus 1. So that's a irreducible quadratic non-repeated factor. That's a case 3. And then we have x squared plus 4 squared, which is an irreducible quadratic that is repeated. So that's a case 4 term. And then we just combine the things we talked about for each term, so for each case. So dividing by x, that gives us a constant divided by x. Divided by x minus 1 squared, that gives us constant over x minus 1 plus constant over x minus 1 squared. That was case 2. And then dividing by x squared plus 1, that gives us case 3 that we talked about a moment ago. We get constant x plus constant over x squared plus 1. And then dividing by x squared plus 4 squared, that gives us 2 terms. We have constant x plus constant divided by x squared plus 4. And then we have constant x plus constant divided by x squared plus 4 squared. So we need both those powers because we started with a repeated term. Okay, so that completes the picture. And so the new terms that we have to integrate, possibly if it's ax squared plus bx plus c, if there's an x term, we might have to complete the square to bring it to a simpler format. But once we do that, we get things that more or less look like hx plus I divided by x squared plus 4 squared. These are our new terms that we have to understand how to integrate, though they don't tend to happen that often. And it would be pretty much the same steps as we had in case 3. So we would split this along the numerator. We'd end up integrating something that looks like constant divided by x squared plus a squared squared. We would do u equals the inside. So u equals x squared plus a squared. Or we would have I divided by x squared plus a squared squared. We would have, so we'd have to integrate 1 over x squared plus a squared squared. Then we would do x equals a tangent theta. So we have to either use the naive substitution if there is the x on the top, or we have to make a substitution involving tangent theta. Okay, thanks everyone. See you next time.